Welcome. In this video, we build a visual definition of a category step by step. We will use simple pictures with objects, arrows, composition, and identity maps, so the main ideas feel concrete from the very beginning. Here is the roadmap. We will build the definition in 5 pieces: objects, arrows, composition, identity arrows, and the 2 rules that make everything fit together. By the end, expressions like F from A to B and G composed with F should feel much more readable. Step 1 is objects. Objects are the named things in the story. They're the places where arrows can start and end. In different categories, an object might be a set, a space, or a group. For now, just think of an object as a labeled point in the picture. Step 2 adds a single arrow, also called a morphism. The arrow starts at its source and points to its target. In this picture, F goes from A to B. Direction matters, so an arrow from A to B is not the same thing as an arrow from B back to A. This is how to read the notation F from A to B. The letter F names the arrow. A is the starting object, and B is the ending object. So the notation packages together the arrow's name, where it begins, and where it ends. A category is not just one arrow. It is a whole network of objects and arrows, like the diagram on the left. Category theory asks which arrows exist between objects and how those arrows fit together into a coherent structure. Now, suppose we follow 2 arrows in a row. If the target of the first arrow matches the source of the second, then the 2 steps can be chained together. Here we move from A to B using F, and then from B to C using G. Composition turns that 2-step journey into a new single arrow. Following F and then G creates the composite arrow G, composed with F from A to C. The order is read from right to left, first F, then G. Every object also gets a special arrow called its identity arrow. For object A, this is the identity on A, from a back to A. It is nothing. It starts at A, ends at A, and leaves everything unchanged along the way. Now the pieces are on the table: objects, arrows between objects, composition, and identity arrows. At this point, we almost have a category. The last ingredient is a pair of rules that tell us how composition and identities must behave. The first rule is associativity. If we compose 3 arrows F, G, and H in sequence, we are allowed to group them in different ways. We can first compose G with F, or first compose H with G. Either way, the final composite arrow is the same. Associativity changes the parentheses, but not the order of the arrows. The second rule is the identity law. Composing with an identity arrow changes nothing. Doing the identity first and then F still gives F. Doing F and then the identity at the end also gives F. Identity arrows are perfect do-nothing moves. Now let's see a real category: set. In set, the objects are sets, and the arrows are functions between sets. So when we write F from X to Y, we mean that F is a function that takes elements of X and sends them into Y. Composition in set looks exactly like the abstract picture. Here, F sends element from X to Y, and G sends elements from Y to Z. The violet arrow shows the single composed function G after F from X to Z. In this example, 1 maps to red and 2 maps to blue. Here is a longer chain in set. The sets are X, Y, Z, and W, with functions F, G, and H between them. Tracing each element across the row shows the full composite. 1 ends at 1, 2 ends at 0, and 3 also ends at 0. The diagram lets us read the composite function directly. Associativity in set says the same thing as before, but now we can check it element by element. Whether we compose G with F first and then apply H, or compose H with G first and then apply F, every input in X gets the same final output in W. Matching outputs mean the 2 composite functions are equal. Identity in set is equally concrete. The identity map on X keeps each element of X fixed, and the identity map on Y keeps each element of Y fixed. So composing F with an identity on either side does not change what F does to any input. We can now state the full definition. A category has objects, arrows between objects, a notion of composition, and an identity arrow for each object. These ingredients must satisfy two rules: associativity of composition and the identity laws. That is the core picture behind the definition of a category.